Okay, so today we're going to be doing an introduction to reactions by looking at a reaction that we're really familiar with. A lot of us have done it before. However, you may not have examined the effect of temperature, and you might also not have actually looked at the physical reaction and what is going on specifically in the reaction. So we are all going to be looking at this doc today. You might want to go ahead and, if you haven't already, make a copy of it, because you will be filling out your own lab information here in your copy of the lab. So is anybody at home got some vinegar and baking soda and going to be doing this experiment at home? Oh yay, Janie May's here to do the experiment with me. So excited. Go ahead and take a seat and we're gonna get started here in 1 second. So if you do have baking soda and vinegar at home and you wanna try this on your own, I would recommend it, just because then we can actually have more than just my data. So we are going to start with the first part of this lab, which is going to be using 3 temperatures of vinegar. I'm gonna have to go get the cold vinegar in a second, but we have very hot vinegar that was just boiling in a coffee cup, but it is nice and hot, so we're gonna do that one first. We also have room temperature vinegar, and then vinegar that's been in the freezer for about 2 hours, so it's not gonna be frozen, hopefully, but will be cold. I don't think vinegar even freezes at normal freezing temperature for water. So what we're going to be doing is recording how long the reaction takes based on these different temperatures. This is a pretty common reaction to do, right? People use this to make volcanoes, to make rockets, all sorts of different things. We're really here just going to be looking at the specific reaction that happens, and also if temperature impacts it. So as a little warm-up question, first, we'll talk about the hypothesis here. We're going to start moving towards doing this thing in science called the null hypothesis, which is what real scientific researchers do. So a null hypothesis means that we assume there's no relationship between our variables. So in this case, we would be assuming that changing the temperature of vinegar is going to do nothing for the reaction time, right? It's going to be the same no matter what. That's what we're going to assume. Now, obviously, we're doing this experiment because we think something is going to be different. Well, I think something is going to be different, right? That's why I created it. So what do you guys think? Is the temperature going to impact the vinegar? Do you think it will cause the reaction to either last longer, shorter, based on the temperature? What do you guys think? Janie May says, baby. So we'll wait on a couple people in the chat to possibly give us an idea here if they think that reaction will be changed by the temperature. And while people are thinking about that, I just used arbitrary amounts here of vinegar and baking soda. It doesn't have to be exactly 1 teaspoon and 2 tablespoons. Abby says, yes, I think temperature will change the reaction. I agree. And what do you guys think? If it's hot vinegar, is it going to go longer or shorter? We may not know, right? And that's actually why we usually do the null hypothesis in science, because we think something is going to be different. We just don't know what it is. Right? So we're going to assume, nope, there's not going to be a change. And then if there is a change, then we can start explaining it. Sebastian says hot will go longer. Yeah, that's what I think, but I don't know. Right? I've never done the different temperatures situation here. So I'm going to do this first one, and then Janie May is going to help me do the other 2. But we're just going to take a little sample of baking soda here. What's that? Oh, hello. We're doing an experiment for chemistry in here. I know, good times, right? Let's see if I can do it. Okay, so we've got a beaker here. You could use any kind of container. We're going to put about a teaspoon of baking soda in. Again, the amounts are not necessarily something that needs to be 100% accurate here, although you want to try to use the same amount each time you do the reaction. So I got about a teaspoon of baking soda, right? This is just normal baking soda that you could buy. And then we have our incredibly hot temperature. You want to confirm that that's nice and warm feeling, right? It was boiling, which I believe vinegar boils much quicker than water, right? But it's somewhere at least above 80 degrees here. So Janie Mae, would you like to be the timer for this one? So we're going to be recording how long the reaction goes. Now, we know that we're going to tell the reaction is happening because why? How can we tell that there's a chemical reaction? Does it say to you, I'm reacting? Kind of, right? There's going to be bubbles, guys. Bubbles will tell us that the reaction is happening. Okay, so I'm going to do 2 tablespoons of vinegar, and we started our timing here, and we're going to record until there are no more bubbles. We still got some lingering bubbles here. It's definitely calming down significantly. It smells nice and vinegary in here. Okay, and this could be a while, right? So we're gonna set this one off to the side. We're gonna keep our eye on it. It's still bubbling, not as ferociously as it was before. I'm gonna ask Janie Mae to keep her eye on that one and let me know when it ends. And at the same time, we're gonna have somebody from home who would like to be a timer. You can time with your phone. All you're gonna do is watch the reaction and time it. It's pretty easy. Thank you, Abby. So Abby is gonna time our room temperature vinegar, right? It's just been sitting in this room, which I believe is around 70 degrees. So I'm gonna angle this one down for you so you can actually hopefully tell, and if you can't tell if it's done bubbling, just let me know. We're gonna add our 2 tablespoons of room temperature vinegar. And we're gonna let that one go. I'm gonna go grab the freezing cold vinegar while these 2 reactions are still kind of continuing here. And we're gonna be looking for that reaction time in seconds. Well, fun fact, vinegar does freeze. How's our hot doing? Is it still going?
Yeah.
Okay. I don't know if you can see this one, Abby, but it is still bubbling. It's probably going to go for a long time as well. So we'll see. At the same time, I have these vinegar slushies so we can do the reaction for cold, which we're going to need another timer. Okay, I'm going to move our room temperature reaction over here onto the left side of the screen, and we'll have our cold on the right side. So cold is going to be a little interesting because this literally is a slushie. But because it's baking soda and vinegar, it still reacts even when I'm putting an ice vinegar on. And oh, I forgot to make someone start timing this. I guess I'll time this one. We'll add about 20 seconds to it. Okay. So while we're waiting for these to finish, right, we're still kind of glancing. It looks like the room temperature one is still bubbling. It's starting to slow down a little bit. I'm not seeing nearly as many bubbles. How's the hot looking? Just a few bubbles? Okay. So notice even when the vinegar was like a vinegar slushy here, it's frozen, we're still getting a reaction, right? Which is actually pretty powerful because a lot of times things won't react if they're cold or if they're too hot, right? They need like a certain temperature, but baking soda vinegar can pretty much react no matter what is going on in terms of temperature, which is cool. Now we're just going to try to figure out if it actually matters the temperature, right? And it might not. I've never done this reaction length before, so we'll see. So while we're waiting, if you're not directly timing and you want to go ahead and take a little glance into the conclusion and analysis section, we're going to talk about specifically what's going on in this reaction. Once we get our results, then you're going to be graphing them, and then we're going to do some molecular building as well. And honestly, this is pretty good real life chemistry example here. A lot of chemistry is waiting around. I had a lab in college, both of my chemistry labs were 4 hours long, right? Because a lot of the time was just waiting for a reaction or waiting for something to crystallize or waiting for whatever to happen. And it sucked because since I couldn't fit it in my normal week, I had to have Saturday morning chemistry lab, which was very early. But yeah, so this is pretty realistic to what real chemists do is sit around and look at bubbles happening and try to find stuff out. All right, cold still going pretty strong. Room temperature barely still reacting here. So the main reason that this reaction is happening is baking soda is a base, right? Sodium bicarbonate is its science name. And baking soda is often used to treat heartburn, right? Oops, I got a window popping up here. So you can actually use baking soda to still an upset stomach, right? Because it is a base. It's also used in a lot of cleaning stuff, right? It's also used in baking. So there's many uses for it. Vinegar is an acid, right? And acids and bases, as we know, are on opposite sides of the pH scale, right? They're going to react. Usually when an acid and the base react, we end up getting a salt and water. That is not really what happens with this reaction, which is why it's so interesting. So there's actually 2 steps. Now, they happen pretty much instantly, right? So it's not like we see one step and then we see another step. But know that there are 2 things happening. The first equation that you can see on your lab, a summary reaction, right, that says NaHCO3 with an S next to it, that is your baking soda. And that S is because that baking soda is a solid. That CH3COOH is our acetic acid or our vinegar, right, and that is a liquid. And we'll even consider the frozen vinegar a liquid because it was still pretty liquidy, even though it's slightly frozen. And the things that are produced here are carbon dioxide gas, right, which we can see. It's being released as bubbles. Water, right, which we maybe can't tell necessarily, but the liquid in there would be water. Again, that's because of that acid-base sort of chemistry, pH canceling each other out. We also get sodium just floating around in the solution. And then we also get this other compound, CH3COO, which is also floating around in the solution. So looking at that summary reaction, these final reaction mixtures that we have here, we'll call them, would they conduct electricity? Let you guys think about that for a second. Would these solutions with the baking soda and vinegar mixed together conduct electricity? Why or why not? Also, dang, we're still got a tiny bit of bubbles going on. Same over there. Well, if these reactions go longer than 20 minutes, then we will just call it 20 minutes. Hopefully we don't get that long. How long are we on for the hot? 11 minutes right now. Okay. We're on about like 6.5 minutes for the room temp and cold. Or no, I don't know where we're on for the room temp. Abby's got that one. Cold, we're on about 6.5 minutes right now. Cold looks like it's slowing down quite a bit though. Okay. So what do you guys think? Can these, we're on 9 minutes, Abby says, yeah. Can these solutions conduct electricity? What do you guys think? You could take a guess here. You could just say yes or no. Maybe you don't know. Why? Sebastian says, I don't think so. So the answer is actually yes, they could. Right? Because anytime that you have ions, which in this case we have Na plus and CH3COO minus, those are considered ions, and ions can conduct electricity, right? That's technically a salt. It's a weird salt and not the normal kind of salt we see in acid-base reactions, but it is still a salt, right? That means electricity could flow through the solution pretty easily. So that's the main summary reaction, right? But that isn't exactly how it happens. We end up getting 2 steps here. So our first step is a double displacement reaction, which you may not have heard about yet. Basically, it kind of means what it sounds like. Double displacement, 2 things switch places. So looking at the formula below, what do you think double displacement means? I kind of told you already. And highlight the compounds that are switching places in 2 colors. Right? If you're doing this online, it should be easy to do it in 2 colors. If you're writing on paper right now, you could circle, star, something like that. But I want you to be thinking about what exactly is switching places. and then we're going to talk about it. I'm going to actually show the document and we'll highlight together. Did it finally stop?
There's tiny.
Tiny bubbles?
Very tiny.
Same with the room temp. Okay, so I'm gonna go ahead and share my screen on the lab itself. I'm still watching this one, Abby. I will let you know when it stops, if it stops. It's pretty close. Oops, I didn't mean to move that guy. In terms of, I barely see any bubbles at this point, just a couple. So hopefully it will be stopping soon. All right, so on the lab itself, all right, you're supposed to look at this equation and figure out what is switching places. So the best way to do this, I would recommend, is to start with the sodium, right? I'm gonna highlight the sodium in blue. We see the sodium here, and we see the sodium here. And, oops, I wanted to highlight it. Why won't it highlight? Oh, I guess I have to do it this way. There we go. Okay, so there's the sodium, right, on both sides of the equation here. And we notice the thing after the sodium looks like it's moving places, right? So we'll do that one in light pink. The HCO3 suddenly ends up where? I don't know, we'll leave that one hanging for now. We see C2H3O2. Let's do that. We're actually gonna use more than 2 colors, I lied. We see that actually joining with the sodium. And then what's interesting is this HCO3 actually combines with one H here to form this whole new compound. Okay, so all I did was color coordinate this so you guys can see sort of what's happening, who's switching places, right? Sodium is going from holding on to this HCO3 to now being combined with C2H3O2, right, which came from here. This H from the vinegar, right, because this is the vinegar that we're looking at, actually ends up separating itself out, which is why vinegar is an acid. Should we highlight it like this? Yes. And that H combines with the bicarbonate part of sodium bicarbonate and forms another type of acid, right? It forms a carbonic acid. So we have a double displacement because both sets here, both our sodium and our vinegar, are essentially switching places with each other so that we get 2 new compounds, if that makes sense. So the only reason I would say to highlight like this is so that you can trace what is happening. Where are the elements going? So carbonic acid is this guy right here, our H2CO3. That is a new acid that is formed, right? We take one H from our vinegar, it combines with the bicarbonate part of the sodium, and it actually becomes an acid. So that acid is super unstable. It actually goes through another type of reaction called a decomposition reaction, and then it produces the bubbles that we see. So both of these reactions happen basically at the same time, which is why we see the bubbles almost immediately. I think we can call that these are done. There's barely any bubbling going on my two, and I don't see very much going on there. So we're going to call the time now, because they all at least seem to be bubbling at the same rate now, which is not as intensely. So go ahead and pause your stopwatch there, Abby, and let's see what we can fill in for our data. So our ice-cold vinegar reaction time was 13 minutes. Well, we want to do this in seconds, right? So how many seconds is 13 minutes? Let's see. $780 seconds. 830 seconds. All right, and what about room temperature? We got 1649. So to make that into seconds, we're going to multiply 16 minutes times 60, right? Because we have 60 seconds in a minute. And then we're going to add our other seconds plus 49. So 1,009 seconds. And then our hot, we ended up with 18 minutes and 48 seconds. So we're going to do 18 minutes times 60 seconds to get 1,080 and plus 18. We get 1,098 seconds. Okay, and again, they're still technically reacting at this point, right? But all of them are barely producing any bubbles. So we're going to call it as an end just because they're all pretty much reacting at the same rate at this point. And they would most likely continue for, who knows, another like 15, 20 minutes, possibly. All right, so, and of course, if you move them around too, then they'll start reacting more. It's pretty interesting stuff there. All right, so back to the reaction. So yeah, then this carbonic acid actually decomposes. So just looking at what's happening in the decomposition part of the reaction, what do you guys think decomposition means? Or what does the word decomposition mean that you think we could apply to chemistry here? Yeah, to like break down, to become smaller parts, right? So anytime you see a decomposition reaction, you always see one thing breaking into smaller things. It's decomposing. Right? Usually in decomposition reactions, we have at least one gas produced. Not always the case, but usually. So in this case, that carbonic acid is actually breaking down into water and carbon dioxide. So that means that at the end, when this whole thing is done, if we were to sample this solution, we would have water and we have a bunch of ions dissolved in there, right? We have sodium dissolved in there and we have the, I don't know what that ion is called, the H3COO minus. I'm not 100% on what that ion's called, but we have those two ions in our water, right? And then the bubbles are carbon dioxide. So if we left this for a few days, all the carbon dioxide would be gone. And we would just have basically a salt dissolved in water, which is pretty cool. So that's kind of how this reaction actually works. I know that a lot of us have probably mixed baking soda and vinegar before, but maybe not understood 100% what's going on in terms of elements in chemistry, right? So that's kind of breaking it down into the steps and the reaction that actually happens. Usually when we combine an acid and a base, there's not two parts, right? It just immediately becomes water and a salt, which is why if you ever in a chemistry lab spill an acid, the way to clean it up is to pour a base on it, right? Then it's going to become water, and then it's not harmless. Then it's harmless, excuse me, instead of harmful. Okay, so you're going to do the conclusion questions on your own, but you're going to either accept the null hypothesis that there's no difference between the temperatures, or you're going to reject it and say there is a difference between the temperatures. Why? That's going to be totally your own thoughts. I would think about energy, right? Potentially, if something's hotter, it has more energy between its molecules. That might be something that you could say. You're going to graph the results on a line graph, and you're going to use your graph to predict two temperatures, right? By the way, our temperatures we're going to approximate here, but let me see what the boiling point of vinegar actually is, and the freezing point. So boiling point of vinegar is 244 degrees. It definitely was not that hot because it sat for a few seconds. So we'll say that the hot vinegar was around 180 degrees. I'm going to approximate here. Our room temp vinegar was around 75 degrees. Probably a little colder actually, 70 degrees. And our freezing vinegar, what's the freezing point of vinegar? Ah, look at that, it's 28 degrees, 4 degrees lower than water. It's pretty cool. So 28 degrees because it was frozen there. All right, so those are our three temperatures in, common terms and actual degrees there. That way you can do your graph. And then the last part is really to explain the reactions in your own words. And eventually we're going to get to talking about single replacement reactions. And actually there's a whole list of them, right? So we're going to go through all the different kinds, but keep in mind this was an example of acid-base in some ways, double displacement, and decomposition. That's why it's an amazing reaction, because it shows so much. Okay, so then part two was this molecular building. I know a lot of people did the Lewis structure assignment already, where they either built things or drew the molecules, but we have this awesome molecule building kit here. And we're going to try to build sodium and vinegar, possibly, hopefully. I don't know if sodium is even included in this kit. Probably should have checked that. And if you're at home, you're going to try to draw them, right? Or build them using things that you have next to you. And we don't have sodium. So we'll just have to imagine sodium. So Janie Mae and I are going to play with the molecular kit here. This is what it looks like. It's just a bunch of balls with holes and different bond stems here. And we'll check out the instructions briefly here because I think certain things are. So these are the colors of our different atoms, and these are the bond sizes. We have short, medium, and long. So our long ones are supposed to be double bonds. These are supposed to be single and single or space filling models, so when there's no space between them. So really short and medium don't matter, but long will be our double bonds. Okay, so let's see. If we want to try to do sodium, we don't have a sodium molecule, so we'll have to pretend that we have a sodium. But we're going to need a hydrogen, a carbon, and 3 oxygens. So 3 oxygens, carbon, hydrogen, and then we'll pretend that we can attach a sodium as well. So sodium is going to have how many valence electrons? People at home. How many valence electrons does sodium have? We'll start building while we wait for you guys to tell us about sodium. So, do you think carbon is going to be the center for this? Probably, right? Okay, so these are our double bonds. I'm going to try to build it too. So if you're at home, you should be trying to draw the molecular structure of baking soda or sodium bicarbonate, which is our first example. Thank you, Abby, who says 1 valence electron. I guess Abby's the only person paying attention to me. Thank you, Abby. I appreciate that. And by the way, I picked hard molecules for you guys to draw here, right? So if you end up having to look up how to draw these, and then you can use that to explain to yourself how to do it, that's also fine, right? Just make sure you understand why we're seeing what we're seeing. In fact, I'm going to check my answer before I explain it. Oh, interesting. Okay, I was slightly wrong here. Things hard to take apart. Okay, so I'm going to explain this one, and then, like I said, if you guys need to look up these structures, because they are really hard, and then explain to yourself how to build it, that is totally fine, right? Because a lot of this comes from seeing tons of molecules. You're going to start kind of seeing how they work. So for this one, carbon is our central atom, right? Carbon is our black atom here. Carbon has 4 valence electrons, right? So we need to see 4 lines coming out of carbon, right? 4 bonds. It's going to double bond with 2 oxygens. So 2 valence electrons are going to be for this oxygen, and 2 valence electrons are going to be for this oxygen. It's going to single bond with 1 oxygen, and that oxygen is also going to single bond with a hydrogen. That's a really common relationship. If you ever see a CH and an O as part of a molecule, that's usually what it means, is that the oxygen is bound to the hydrogen and the carbon, right? Oxygen needs 2 valence electrons, hydrogen can give it 1, carbon can give it 1. Now, this other oxygen that's double bound to the carbon, because of this entire molecule here, it actually ends up taking on a negative charge and bonding with a sodium, which sodium isn't in this kit, but I'm going to pretend that this green thing represents sodium. So the sodium is not really bound in a covalent way, so it's kind of hard to show in a molecular kit, right? But essentially the sodium would be positive charged, the oxygen would be negative charged, and they'll be next to each other. And that's what baking soda looks like, right? It has a neutral charge because the sodium and the oxygen are ionically bound essentially, and the rest of the molecule is covalently bound, which is very confusing, right? So if we look at what this looks like on, like if you Google this, right? What does the structure look like? We end up seeing pictures of what I just explained, right? So, oh, excuse me, this is not a double bond. It's only a single bond. That's why. I was going to say, how is it negative? Because it's a single bond. So that carbon is single bound to 2 oxygens and double bound to 1, right? So in terms of chemistry, what does that mean? Right? That means that carbon has 1, 2, 3, 4 bonds. Carbon is satisfied here. Oxygen is satisfied. It needs 2 bonds, right? It has 2 valence electrons. That's literally how I think about it, is how many bonds do these things need? Here, oxygen is bound to a hydrogen and to a carbon, so this oxygen is satisfied. This oxygen is not. It is single bound to a carbon. It has a negative charge, right? It's going to attract that sodium, but after the sodium donates an electron to that oxygen, and we're going to have an ionic bond, and then the rest of the molecule is covalently bound, which is very confusing, right? So again, if you try to build it and you're like, I'm not sure, is this double bound, single bound? I don't know what's going on, right? Google it and look at the structure and then explain it to yourself. How does this actually look and how does it work? And check the valence electrons, right? Oxygen has 2 valence electrons. Only one of them is in a bond. The other one here is negative, which attracts it to our sodium. Okay, so Janie May and I are going to continue. We're going to try to build a couple other molecules. I want you to try to build 3 of the following molecules, right? So there's 1, 2, 3, 4, 5 choices there. We just built the sodium bicarbonate together, so that's awesome. You need to build 2 more. Otherwise, I'm going to end the session here. The code word for today is in the chat. So include that code word on the lab, right, to get full credit for being here in the virtual session. And if you get stuck on trying to build one of these things, like I said, always start with carbon in the center, right? And if you're like, I don't know what else to do, Google it and then explain it to yourself. Why is it that way? Why are they bonding the way that you're seeing, right? Because like I said, as you're starting out here, you're going to want to just see as many molecules as you can, and you're going to start seeing patterns. Okay? So if you have any questions, feel free to email me, right? Otherwise, the lab, really all you have left to do is the graphing and the conclusion questions, and then to draw some of those molecules. All right, so I'll see you guys the week after Thanksgiving.